Ground station control is developed to achieve our autonomous mission. By integration with obstacle avoidance and image processing, an accurate autonomous mission will be developed.
The Wi-Fi link has improved for the aircraft communication system by using the Bullet AC with its new software AirOS 8, connected to the NanoStation AC, which is chosen on the GCS with its gain 16 dBi. The new microcomputer Raspberry Pi 4 is used on board, uploaded with audio cam and connected to the GCS by using the real VNC.
We use Pixhawk 2.1 FC for autopilot control. Wiring and the power of our UAV are studied and calculated to get high score for the mission. All electrical system is tested to fit the rules.
After studying the rules and taking consideration the constraint, we have determined the design requirements. So, we have made the primary design of wing and tail, and the structural design task completes the rest of the work.
After taking consideration the flight performance, this year we changed the airfoil to Epler 207 to get the best performance and to achieve the highest rate of climb.
This year we have been working on some changes. First, we used YOLO V7 instead of YOLO V5. Second, we changed our camera to Raspberry Pi high quality cam. Looking at the training section, we used a dataset of about 45,000 images to train our model to get efficient detection.
This year, we are using a new obstacle avoiding system using a stereo Pi and two Raspberry Pi high-quality cameras to apply stereo vision to detect moving obstacles. We also add some modification to Mission Planner to avoid stationary obstacles.
We've been working on the design, seeking for the highest score, trying to achieve the maximum number of tasks, taking into consideration the weight and size constraints.
The main structure of the wing consists of two longitudinal bolts and ribs of plywood designed to carry bending stress, with balsa wood for while the complicated parts are 3D printed. A high wing configuration is designed to ensure high degree of stability and to limit induced drag. Carbon fiber rods are used to connect the tail and the wing with the fuselage, as it has high tensile strength, stiffness. The aircraft is a fixed wing polar UAV. It's been designed to launch and land autonomously with landing gear to simplify the AAV movement on the ground. Developing a stable and high-performing UAV necessitates a precise aerodynamic analysis to generate the highest possible lift with minimal drag. It was necessary to select an airfoil showing suitable lift derivation for a power loading of 0.0144 horsepower per newton and wing loading of 98 newton per meter square. The optimal wing area is obtained from the curve shown in figure 1A. Analysis is carried out using SUAS software to obtain UAV polar curves as shown. In order to properly locate both CG and neutral point initially located. For a static margin of 10% of CG found to be 32.3% of the coordinates measured from the leading edge, which is the optimal location, ensuring both stability and performance. In ODLC, we were given two tasks. The first one was to recognize shapes with an alphabet written on it, both having different colors, and provides its data besides its geolocation. The second task was to recognize people in urgent situations and provide their geolocation. For that, we decided to change our vision system from using Canon EOS M50 to using Raspberry Pi high-quality cam to be more compatible with our communication system and therefore give results faster. Also in computer training section, we chose YOLO because its accuracy and speed over other training algorithms. This is helpful in life stream detection while moving with high speeds as planes. We already use YOLO V5 in the last season. By now, we upgraded from YOLO 5 to YOLO V7. Thus, we have more accurate and faster results. To start training, we had to get a dataset ready. For that, we use custom-made code to generate a dataset if it was real footage using OpenCV library. So that our code could detect real photos after training and making sure that its dataset is compatible with YOLO V7. After training, we went through to editing our detection code using Python and some mathematical equation to give us both classification and localization results in the most desirable format. Compared to the last year requirements of the competition, the payload was much lighter, smaller, with less stages of drop. We had the problem of dropping the payload on stages, so we figured out a new dropping mechanism. And about the size of the params, it were much larger than the last year's payload, which was AGV. On the other hand, to secure a smooth drop-in with the drop-in requirements, the airdrop housing and mechanism were designed in a new simple way. Safety pilot communication. In case of manual takeover, 14 channel FOTAPA transmitter, 14 SGA, and FOTAPA receiver R708 SP are chosen, which provide 3-mile range. The system uses frequency open space spectrum protocol that transmits radio signals at frequency 2.4 MHz, which suits the mission requirement. Telemetry communication. Using RFD 900X telemetry module that provides long range more than 40 km with high power, more than 30 dBm, and advanced encryption standard hardware accelerated encryption to send and receive autopilot data with pair of dipole antenna of 8 dBi perpendicular to each other to achieve signal polarization operated at 902 to 928 MHz frequency band and high data rate of 500 kilobytes per second, which provides a telemetry rate of 1 Hz smoothly. For the onboard communication system, the Wi-Fi link has been improved by using Bullet AC with its new software, AirOS 8, which provides dual band frequency using 8 dBi omnidirectional. Raspberry Pi is controlled on board using VNC Viewer or PySource Shell protocol. From the GCS, and images are transferred by Transmission Control Protocol antenna. And it's based on new AirMax AC technology, which provides maximum channel bandwidth of 80 MHz with high data rate of plus 300 megabytes per second. For redundant telemetry, PX4 is better than PX Cube as shown, but Pixahawk Cube is used as it fits the mission requirements with lower cost, and Pixahawk isn't tested and tuned. The team isn't prepared to use it. For UAV real-time mission data visualization, our choice was Mission Planner GUI, as it's compatible with Pixahawk Cube Mapping Protocol, as the Mission Planner is an open source code which provides accessibility to it alone. We might include a few critical functions to assist us in our missions, particularly at static and dynamic obstacle avoidance missions, by including GUI strategies to do the mission. Draw the obstacles as circular shapes, through the geofence, and avoid obstacles to produce a new path using an algorithm described afterward to ensure a safe autonomous mission flight for a fixed-wing UAV. Autonomous takeoff and landing is established by controlling the ascending rate of UAV as well as descending rate of landing. Our UAV is reliable for autonomous flight with respect to the waypoints navigation, image capturing, and payload drop, then safely return to ground. GEC is keeping communication between UAV to ensure continuous receiving of data, images of obstacles, or ODLC, and telemetry. Decision making depends on the images captured by dynamic obstacles or ODLC or any other images required. For autopilot, we use Pixahawk 2.1 Cube, here 2 GPS, RFD 900X, Raspberry Pi 4 for communication, a Stereo Pi version 2.02 for obstacle avoidance, 9000 RPM motor, and 11,000 mAh 40 cell batteries, and all cables used are AWG cables. Stationary obstacle avoidance. After the roughly comparing rapidly random exploring tree, A-star, and tangent algorithm. After running all these algorithms in the obstacle avoidance mission, tangent algorithm was chosen as it passes the mission with high accuracy and short execution time. If the path had an intersection with an obstacle, the algorithm calculates the tangent and adds a fixed safety distance and create another waypoint between the two original points, and with a smooth path as much as possible. After adding the new waypoints, the algorithm continued to the next points to see if there is any intersection with the other obstacles. Moving obstacle avoidance. We are using stereo vision applied by two Raspberry Pi high-quality cameras to detect the moving obstacles, the other UAVs, using OpenCV library in Python and avoided through some modifications that were added to the mission planner source code under some conditions. Maximum height 380 feet, minimum height 100 feet. As if another UAV enters the safety distance, one of these actions is taken. First situation. If our UAV is above the other UAV, it will rise 20 feet more without exceeding the maximum height. Second situation. If our UAV is below the other UAV and above 120 feet high, it will descend 20 feet. The third situation. If our UAV is below the other UAV and under the 120 feet high, it will create a point as a guided point and our UAV will simply go to it for a fixed time, then return to the path and continue the mission. As shown in video, we made a stress analysis on the wing on ANSYS software, so we made sure that it's safe to fly.